No one wants to learn about control, huh? That's the best part. Alright then. Sorry, I had to cut you off last time. Last quarter, I went overtime and they complained to my boss and they told me I can't do that anymore. This woman in the geography department. Oh, sorry. She's very upset with me. So, yeah, he like what, dude? Yeah, exactly. It's very eager. He loves knowledge too much. Oh, I guess this is being recorded. Oh, yes. Oh, yeah, represents. Okay. Give it like 2 minutes. How's your hours homework too? Good.
That's not too bad. I looked at it like.
Oof. Reinforcement learning doesn't look too bad either. I've been spending 10 years on it. Doesn't work. You should try it earlier rather than later.
Yeah.
Is it due on this?
The second. 3 or 31st. Not good.
See, like, it's not bad.
Okay. It's not bad. You should just take some time to
I
do
don't
it.
know, it's like, I can't remember one pie. I feel like once it's like taking some of the slides, kind of implementing it, so.
Okay,
yeah, we'll see.
I'll fix it on the website. Thank you for that. All right, sure.
Oh, you?
Yeah, unless you want to do it.
We have group 2 finishing up the presentation and then we'll talk about feedback.
Yeah, so briefly we can talk about limitations. The main thing that talked about all the specimen paper is that KLD sampling is based on fixed bin size. This requires nothing but a fixed bin size. And for performance, we'd like to have a way to like adapt the bin size, so we want it larger when we have high uncertainty, and then decrease the bin size as we get more confident. And then these are 2 papers which use KLD sampling but with an adaptive bin size. And my first paper used it because they found that not like starting with a very small bin size, that's increase in the particles they need to start with. And then the second paper demonstrated both in experiment and simulation that having adaptive bin size increased the performance. And then the other limitation that Marcel talked about was that samples must be drawn from the true posterior distribution, which is not always true for all applications of KLD. So there's some work that people did with KLD recent, which doesn't allow this assumption. Yeah, and then for feature work, they talk about 2 things. I talked about considering this the state space as well as the like KLD distance. One, considering choosing the sample size. So if we're in a situation where maybe we don't actually need a super accurate estimate, then maybe we can decrease the number of samples, or if we're in a place where we're really worried about accuracy, we can increase the sample size. And they suggested using multi-resolution tree structures to manage that map of the state space. And the other thing they talked about was how this would perform in real life, so managing performance and accuracy when the rate of sensor data that we're getting in outpaces the rate that the particles are being update. So that sort of leads to a decision about like what sensor data should we discard and like how does this affect how we choose a good sample size. Yeah, and those are the main things.
So I'm curious on, you're saying that you want to change number of particles based on the downstream application, like to control or something. How do you, is there a way to factor in not just the safe phase size, but like let's say you have like a really coarse system, you're in a truck, driving around versus you have like a surgical robot, the accuracy needed will be different. And so KLD sampling chooses the epsilon, right? How do you have a sense for how we might choose the epsilon? Is it like hand chosen, or is there a way to get it automatically?
I'm not really sure.
I mean, if I had to like just take a stab in the dark here, I'm sure if you like reduce that size delta for the bin sizes,
Hmm.
because that kind of correlates directly with sort of epsilon and that sort of approximation equation, is that?
Yeah, that could be one way. I guess it's also just like maybe trying to understand the tolerance of the downstream application. Like for instance, um, if you can understand if my model was wrong, if my state was wrong, but my value function or my action kind of remains the same, then I don't need to be that. So you can make the bins bigger. So like when you're doing downstream control or planning or whatever, if you could say that force control and fine control will be the same answer, then you could probably make the bins bigger. But yeah, cool.
So talking about like some of the appreciation for the research paper, there is a lot of transparency in the computational power required to carry out the experiments. So like, I guess in the captions underneath a lot of the experiments, they described what you could carry it out, like what type of PC, like a low end PC. I guess that's still kind of a vague term, but you can tell that it's not as computationally memory intensive as maybe something that is a more intense algorithm. And then also they performed it on different environments. So the experiment performed previously was on something very symmetrical. And so they gave one experiment performance data set on a more symmetrical kind of map. And then later on in the paper, they didn't have another map of it, but they kind of talked about doing more global localization experiments with different conditions. And so I thought that was like a good comparison because symmetric environment is something very different than like a very convoluted terrain or something like that. And then also I thought that the pseudocode format from this earlier slide, they kind of wrote it with comments. I don't know. I thought it was easier to understand. It was just something that I appreciated that they did in the paper. And then also, I also thought it was interesting that they kind of put error bars in like the average number of sample, the right side graph. It kind of gives 2 points of comparison. There's one accuracy, which is like, you can see the error bars for the KLV sampling is a lot smaller height wise than those for likelihood-based adaptation and fixed sampling. And then there's also obviously like KLV sampling data point itself reaching the lowest error, which shows like there's accuracy, and then there's also like I guess just the overall experiment. And then so follow-up work that is interesting to know, there was actually like the 2013 follow-up work that was dealing with KLD resampling. And so just a reminder, KLD sampling is basically a method that generates samples from a distribution to minimize the KL divergence between the generated samples and then the target true posterior distribution. And so basically, from my understanding of that paper, is they took that method and did resampling with it to determine the number of particles to resample based off of the KL measure fit of the posterior distribution. I actually pulled the two graphs from it. Kind of my key takeaways from this was, even though you can see that it kind of maintains close estimation accuracy to the KLD sampling and the basic particle filter, which is the SIRPF. The SIRPF is what happens when you have like a set number of particles, like you're not adjusting bin size or sample size or anything like that. But then here in this circled area, there's the resampling method, kind of the blue one adjusts the sample size more efficiently, while the KLD sampling generates more particles when the estimation quality is reduced. So in other terms, the particles aren't as effective in capturing the true distribution, and there's a lot of like variability in the mean number of particles as it tries to adjust and then eventually converges to a more stable mean number of particles. So yeah, I also saw that it actually takes longer for the KLB resampling to converge to that same number of like set particles, but they didn't really talk about that in the paper, but I don't know. I think the key point is the variability in the number of particles at the very start as it's getting adjusting. It's adjusting to eventually converging to a set number. And then the other paper I saw was like the underwater terrain navigation paper that was mentioned earlier. So it used an improved KLD particle filter with a variable bin size, but as you can kind of imagine, kind of ambiguous, constantly changing underwater terrain can make it really inefficient to maintain a fixed number of particles. So they ended up changing the bin size, which also varies like the number of particles used. So maybe place areas of terrain where there's more intricate features or constantly changing states. They can increase the bin size versus easier terrain, decrease bin size, and also kind of being able to vary the bin size decreases the chance of there being I can't remember the exact term, but like making the distribution too narrow-minded. Yeah, a little bit, like only adapting it to one specific terrain when in reality there's constantly changing elements and all that stuff. So yeah, that was the follow-up work. And there's an appendix here.
Awesome, thank you. Any questions? Okay, well, thank you, Gupta. I guess we'll have our next paper reading in like a couple of weeks, but for now, we'll kind of move to control. And let's see. Okay, well, let's start from some logistics. So homework 2 is due on Feb 2nd. I think the website might be a little wrong. But yeah, Feb 2nd. And if you need more time, it's fine. Just let me know. It's not a big deal. The reading responses are due on Monday. Just try to pick one of the papers and say something that you found interesting about it. And you don't have to stick to the prompts if you don't feel like they're the most interesting questions. But I just want to hear your thoughts on the paper. Right? And I know a lot of you haven't started the homework yet, but please do. It's like it takes a little bit of time to get the tuning right. And so like start it earlier rather than later. We have one guest lecturer coming from Toyota Research who's going to talk about imitation learning. And we have one guest lecture slot open. So if you want to invite someone famous, let me know. Because famous people take 3 weeks to respond on email. So now's the time. Yeah, let me know. Okay, so to kind of figure out where we are in the class, we finished state estimation. So congrats to everyone for making it through Kalman filtering and particle filtering and the whole thing. And we won't have to visit it until later. But what we covered so far is we started with robotic system design. We went through the idea of Bayesian filtering, and then we instantiated the Bayesian filter as things like a Kalman filter, which is linear and Gaussian, a particle filter, which is nonlinear, non-Gaussian, and some extensions. Right? And so let's try and understand how to go from state estimation to control. So we're going to go to control, then to planning, then to learning. Right? And so the outline of today's class is we're going to try and figure out what does control mean, and where does it fit in the roadmap? And then we're going to ask whether control problems are hard, and if they're not hard, we'll just skip the next 3 weeks. And then we'll think about how to formulate control problems. Okay. So go back to, if you remember lecture 2, right? We started with this helicopter. The helicopter has some sensor readings, some LiDARs, GPS, and it has to interact with the environment. It has to output actuators, right? And so we went down this rabbit hole. Let's come back to the robotic system design and see where everything fits. So we started by saying we're going to define a world model, and the world model describes how the world works. And so it's what we described as our motion model and our sensor model. What we talked about so far is how to use our measurements and actions in the world to figure out where we are. So we've tried to figure out how to get the inputs into our world model. And so that is what state estimation is. And then once you have state estimation, then you need to do planning, which is trying to say, okay, you want to accomplish some goals. You want to land your helicopter in San Diego, and you want to figure out the set of steps to get there, navigating around obstacles, and you want to do planning, right? The planning is figuring out the path you want to take, which obeys some constraints, and gets you there under the kinematic constraints of the robot, right? You can't just like magically fly through mountains and so on. And then we're going to have control, which is saying, given a plan, given a course plan of how to get from here to San Diego, how do we instantiate this in terms of joystick controls on the helicopter? And so where we're at is, so far we've described this whole wonderful layout, but we've only really figured out where we are in the world, right? And what we need to figure out is how to plan. So how do we figure out how to plan a path from here to San Diego, which is obeying constraints and avoiding obstacles and so on. And then how do we take that plan and instantiate it in terms of control, which is like the low-level controls that are going to go on your system. And so we've solved where we are. Let's think about planning and control. Okay, so we're going to go back to our sense, plan, act paradigm. We start by estimating robot state. So you want to estimate where you are in the world, even though you don't have accurate sensor readings. We then want to plan a sequence of motions. So you want to get around these obstacles, planning a sequence of motions, and then control is going to figure out how to follow this plan. And for the sake of the next 2 weeks or so, we're going to say, hey, we spent the first 3 weeks of our class trying to estimate robot state. So we're going to call that done for now. We're going to say we have some rough idea of where we are in the world. For the sake of the next 2 weeks, we're going to assume that there is a plan that is given to us, right? Someone has done the planning, Magic Oracle has done the planning, and it's told us kind of the rough set of waypoints that you want to follow. And what we're going to think about next is, given an estimate of the state where you are, given the set of given the set of waypoints that you want to follow, the plan that you want to follow, how do you actually control the low-level robot to follow those waypoints, right? And so we're going to assume that you know state estimation. We want to assume that you have been given a plan, and then we're going to learn how to do, or we're going to learn how to do control, right? And then in the weeks after that, we're going to figure out how to do planning, right? And then you have all the pieces that you do. Okay, any questions? Great. So the gap from state estimation to control, right? So state estimation is kind of the same problem as perception. We're trying to figure out where you are in the world, what are the things in the world from sensor readings. But it's a very passive problem, right? You were just in the world, the sensor readings kept coming. Someone even told you what actions you were taking, but you didn't do anything proactive when you were taking the actions. You just took the actions and you tried to estimate where you were. What we're going to do in control is we're going to go from this passive system to something that's active. Right? So in state estimation, like something drives your car around, like a human drives your car around. You try to estimate where you are. In control, you are the algorithm is the thing that is going to drive the car around. So it's like going from the passenger seat to the driver's seat. And so in everything that we've done so far, we assume that U and Z were just coming to us, right? And what we're going to do here is we're going to choose the U. So an example of control that is compelling is this example of like high-speed parking. So this is what we expect you to have by the end of the quarter. But they're trying to do like high-speed reverse parallel parking, right? So they're trying to do like extremely tight parallel parking, and you can see the difficult control problem is being quite accurate in how he moves under drift, under grade. You can see the floors wet, right? And so hopefully the power of CSE 478, you can do this too. So that's what when we think about control, we want to do problems like this, problems where the dynamics are non-trivial, problems where you have to be pretty accurate. And so we're going to try to think about the basic techniques that could do this autonomously. Right? So before we figure out how to do control, we need to think about what is control, right? So control is saying that you have a plan, you want to get to actuator commands, you're just going to try and figure out a mapping from your current state and your plan to what commands to take into it, right? So you're trying to say, you're given an X or an estimate of X, you're given a reference trajectory that you want to follow, you want to figure out what the hell to send to your actuators to accomplish this, right? Okay. So before we define control, we said control is trying to go from a plan to actuator, but what the hell is a plan, right?
So we haven't even defined that. So what we're going to use the plan to be here is we're going to say you have your race car, right? At time step b naught, you're going to have the state of the race car being x naught, y naught, and theta naught, right? And then you're going to say that your planner gives you a sequence of waypoints that you want to hit, right? So let's say that D1, you want it to be at x1, y1, theta 1, at D2, you want it to be x2, y2, theta 2, and so on, right? So it gives you a reference trajectory. Well, this is just a discretized version of a trajectory, but you can like think of an interpolation between these points as a path, right? So these are just waypoints along the path, but you can interpolate between these to get a smooth trajectory, right? And that could be like something that is continuous in time. So you can either choose it to be discrete or to be continuous. And to go from discrete to continuous, you just need to interpolate between the different things. Think of like linear interpolation between the waypoints. There's like smarter ways to do it, but you essentially want to follow this path, right? And that's what your plan is. Okay, but this, if you notice, this path doesn't tell us any actions. This path just says, these are the states you want to be at different points of time, right? And so it still doesn't tell us how to solve the control problem, just like where should you go in the world, but not how to get there. Okay, so we're going to call this, the sequence of x's, y's, and thetas over time, like trajectory, right? It could be a continuous trajectory where it's a continuous function of time, or a discrete trajectory, which is saying what are x, y, and theta at different points of time, right? And we want to follow this reference trajectory. Now, let's say we had a way to go from your current state and your reference plan to get an action, right? And you just like computed the series of actions that took you from x naught, y naught, theta naught to xt, yt, theta t, right? And I just like played those. I like computed them offline and I just ran them one after the other. Like, why is that a terrible idea? Or is it not? What do you think?
Then you start like drifting away from the plan, the
Exactly.
just being positive feedback loops.
Exactly. So you start drifting away from the plan, and then you start getting catastrophic, horrible behavior, right? So the point is that your model of the world wasn't perfect. The world is also unpredictable and stochastic, right? So you're going to take a step. The step is not going to do what you expect. And if you keep computing, or if you keep playing the plans that you computed offline, you're going to reach something completely different than where you intended to reach, right? And so the problem with this scheme of computing actions offline and playing them is that you have compounding error, right? So you have continuously compounding error because of stochasticity and like modeling error in the world. So this is what you call open loop control, right? And so we're going to have accumulating errors. So if, for those of you who are interested in things like imitation learning also suffers from similar problems, right? Imitation learning, you keep having compounding errors, but you keep drifting off the path. It's a similar problem. But what we're going to try and do is something called feedback control, right? So feedback control is saying, you're not going to just play the series of actions open loop. Instead, every so often, you're going to see where am I in the world, where was I supposed to be, and try to recorrect your action or your series of actions that you want to take so that you go back to where you were supposed to, right? So you drifted, now you're like, oh, shit, I drifted. Let me try and recompute my plan in light of this drift so that I continuously get feedback from the world, right? So all that feedback control is saying is that you want to measure the difference between the reference state or the reference trajectory that you want to get to and where you actually are, and keep recomputing your plan rather than have your plan be decided beforehand and fixed. And so, or recompute your actions rather than right? So you're not going to change your plan. The plan is the plan, but you're going to recompute your actions as soon as you drift off the plan. And so you want to measure the error and you want to kind of minimize the error. Okay? And so you can see here that you have an error graph, you want to minimize it. Now, if you just look at this graph a little more carefully, you can see it's like, it doesn't just like go straight to zero. Right? Why is that? Like, why is it not trivial to send a system straight to zero error? So what I mean is you have a system, it's drifted off the path, right? We realize, okay, I was supposed to go here. Now I'm here. I'm like, okay, well, if I do the left, I should probably go more to the right. But why is it hard to get the system back to zero error? Exactly. Yeah. So if you're trying to go back, but your step size is too big, you overshoot, you end up on the other side, you have a big error. Or if in the process of correcting your error, you have more error, right? You might have this repeating, and so it's like not a trivial process to do feedback control, and that's why there's a whole community. That a lot of control theory is really just trying to figure out how to stabilize the system around the reference. And so if you look at any control theory book, they're usually trying to stabilize around zero. Right, so they define a nominal point 0, and they just want to stabilize your system around 0 in the presence of disturbances and so on. Okay, does this make sense? Any questions? Okay, so one way I find useful to think about control is that it's kind of like, it's not just like a plan is like a path through the world, right? And a control law or feedback control is like field. And so what it means is that it doesn't just tell you one path through the world. Instead, it tells you a control law saying that if you were here, you would come back here. If you were here, you would come back here. If you're here, you would come back here. Right? So it's like more like a law. It's more like a field than it is like a trajectory, right? And so you can think of planning like a trajectory and control like a force field, right? Which is sending you back to that trajectory of interest. Okay. Does that make sense? Okay, let's try and get a little more concrete with it, right? So let's think about whether this is a hard problem. And so I've told you this is a hard problem, but I might be lying, right? So let's try and look at what's happening here. So this is a video from some industrial robotic settings, and you can see that they are super accurate, right? They're doing like insertion of really fine pieces. They're doing like extremely precise control. They're like assembling watches and cars and boxes and so on, right? So why is control a problem? I talked to you about all of this error stuff and this and that, but like this looks wonderful, right? So what gives? Am I just lying to you, or is there something else? The environment, perfect. So in a lot of these things, we're like trying to make a bunch of assumptions on the environment, right? So the first assumption we're making often is that the system is fully actuated. And then so when I say fully actuated, I mean that like imagine that you had an object, right? Your phone. Like if the phone is completely in your hand and there's force closure, it doesn't move. Like I can completely control the pose of this hand, so it's fully actuated. Now, if I had a system where the phone is like on the table and I'm like pushing it, I don't actually have full control over the system. It's like under actuated, right? So I cannot control the system degrees of freedom directly. And most systems in the world are under actuated, not fully actuated. While the things we did in the factory setting are fully actuated. So that's not great. The second is because it's a factory setting, you can usually control the execution errors and state estimation errors. Also, you're using like $200,000 robot. So if you're using a $5,000 robot or even a $20,000 robot, it's going to have much more execution error. The models are going to be wrong. The hardware is going to be inconsistent, and so you can't control the error the same way. And so that's kind of the issue when you go to problems like, you don't want to make robot arms picket placing. You want to make humanoids hop around. Then the errors are much harder to control, right? So you have a system like a humanoid. It's much harder to model every possible thing that could be happening, right? And so if you don't have feedback control, you often have these humanoids, tumbling off or not being able to stabilize and getting right? And so yeah, by the end of CSE 478, we should be doing backflips too. So, yeah. So the problem is if you look at the the problem of the Atlas backflipping, right? It's not just that you can like magically control the pose of the robot. Really, all you do is at the start, you have some initial motor thrust, right? You're backflipping, you put the motor thrust in, and then the system has to kind of take its own path, right? So there's gravity, there's momentum, there's slip and friction when you apply those forces, and then you do some precise control adjustments on the way. That's what leads to the backflip. And it's not that trivial to figure out what that is for a high degree of freedom system that is under actuated. And so that's what makes this difficult in the first place, is that if you cannot just like magically decide where the robot was, you can't just teleport it, then it's hard to like control it, especially as the degrees of freedom of the system grow and the system becomes nonlinear, right? If the system is nonlinear, it's like hard to know what the controls exactly is. So that's challenge one. Okay, so now let's say we've adopted this mindset that we're gonna do feedback control, right? And we're gonna like, we're doing things in a model-based way, so someone has written down all the physics equations for, you know, a humanoid robot. And we're just gonna solve this ginormous optimization problem of like, what action should I take to feed into this humanoid robot so that it acts, right? I know the like equations of motion, I have like rough ideas of the model of a humanoid robot, like why wouldn't that just magically solve our problem? Or would it? Yeah.
Because you can't really like model everything on the real world.
Perfect, perfect. So you can't model everything about the real world. So an example here is like this helicopter, right? It's trying to do backflips. So you're trying to get this helicopter to do backflips. And it's a particularly challenging problem, right? Because lots of things in this helicopter are unmodeled, right? It's hard to do fluid dynamics. It's hard to model the exact like airflow and turbulence. It's hard to even model exactly the payload of the helicopter because it's changing and might be unknown, right? And so typically what you want to do is, you know, like to skip over the most fun part. Oh no. My PhD advisor actually used to build autonomous helicopters that do backflips and stuff. You should check out his work. But but if I'm trying to build a model of this helicopter, right, it's actually not super trivial because, okay, I can like do basic things on the helicopter, but in the real world, on a windy day, there's like unknown wind in the environment. The payload is not perfectly modeled. Turbulence is not perfectly modeled. Some drag forces are unpredictable. And so it's hard to build an extremely accurate model. So we've talked about how we're going to simplify the modeling assumptions. And so a lot of the times we want to choose a simplified model and add noise to it, and then figure out how to do control robustly by accepting that our model is going to be right. So in the state estimation world, it's not so catastrophic because, okay, I'm a little bit wrong in estimating where I am. But in the control world, it's really important because if you don't account for the fact that your system is noisy and wrong, then you're going to go crash into the wall. It's catastrophic. Right? So the important thing to remember is that accept defeat, and you cannot model the world perfectly. And you have to ensure that you're modeling the fact that there will be noise and disturbance that you cannot perfectly model. And so in most control theory problems, you want to make sure that you're accounting for stochasticity. Like a control problem is not really meaningful unless you have stochasticity. And secondly, I've talked about like optimizing through this model, but if the model is extremely complicated, it's hard to solve optimization problems. Really complicated. Large model is computational. If I'm running a helicopter in real time, I can't solve like a problem that's going to take 10 minutes to compute. I can't do that at like 100 hertz, right? And so you need to make sure that these problems are fast enough to do control quickly on these like reactive dynamic systems. Yeah. So the trick is you want to choose simple models and enough stochasticity so that you can be computationally efficient while still being able to correct from errors, right? Because you model stochasticity. Yes. Okay. And then the last thing is that the model is going to change on the fly, right? So if you have things like a race car, for instance, and someone was saying they want to do battle bots with their race car over the border, it's going to change the dynamics of the race car. It's going to change the friction. It's going to change the mass. It's going to change the like orientation of the wheels. So there will be changes in most models on the fly. And either you can try and re-estimate the parameters of the model, or you can try to do control that is robust for some amount of things, right? And changes in model dynamics. And so this is what makes control challenging and non-trivial, right? These three challenges of having an underactuated system, having complicated models, and models changing on the fly, right? Does that kind of make sense? Okay. So, you know, our goal is not to control helicopters in this class, it's to control race cars, right? And so let's try and instantiate the control problem and the feedback control problem in the context of it. So what I mean by instantiate is we've talked about these abstract terms of feedback control. I want to think through what is the process of like doing feedback control at a particular time step, and like how do we model the error? Like what is the frame of reference? How do we write a control law? And then we'll instantiate these control laws over the next few classes, right? So what we're going to try and do is we're going to try and say we have this path that is given to us, right? by x50, y50, theta, telling you what x, y, and theta should be over time. And you are trying to figure out how to do feedback control across several steps. So the first thing we need to do is we need to figure out what parameterization we should choose for our trajectory in the first place, right? So one option is that you choose a time parameterized trajectory. And what that means is that at time t1, you want to be there, at time t2, you want to be there, at different points along the trajectory, you want to say at time, t1 prime, you want to be here, t1 prime prime, you want to be here, so on and so forth. So you want to say at a particular period of time, you want to be at a particular state, right? And so that's a natural thing to think about. A trajectory is saying at a particular period of time, you want to be at this. Right? So that's good because if you want the robot to, respect time constraints, it's useful. And you have places to get things to do. You don't want the robot to lag behind. But sometimes you don't really care if you get there exactly on time. You care more about getting the reference shape correctly. And so it's okay if you deviate a bit from the time, but you really want to get the shape of the trajectory correctly. Let's say you don't want to hit obstacles. You don't really care if you match the time exactly. And so sometimes not choosing a time parameterized trajectory is useful because it can say, it gives you some leeway on when you will get where. And so if you want it to not be time parameterized, what's a different way to do it? Any ideas? Yeah.
Based on the location.
Based on location, yeah. So essentially, the next way of doing it is essentially index parameterized, which is saying take your path and split it up into a number of pieces, right? Which is saying like take your path and split it up into kind of equidistant pieces, and those are like your indices, right? And you're saying you just need to get to the indices, so you get the shape, but you don't care about getting there at a particular, right? And so the nice part about doing that is that it gives you more flexibility in that you don't have to get there at a particular period of time, but you can't really control when you're going to reach somewhere. So if you're, doing Formula One, that's probably not the right move. But if you're, driving a race car in CSE, it's probably fine. Right? And so I'm not going to be prescriptive about when you use which, but depending on the problem statement that you have, you can try different parameterizations of the reference trajectory, right? Does that make sense? So like usually a planner will give you some set of points that you have to follow, and then you can choose how you want to parameterize the reference, whether it's time indexed or time parameterized or index parameterized. Okay? So that's the first bit. How do we choose a reference parameterization? And once we've chosen the reference parameterization, the process of control looks as follows, right? The process of control says you first choose a reference path or trajectory to track. That's coming from planning, plus you choose a parameterization for it, right? So you figure out what the shape is going to follow. And then you want to pick a reference state. So let's say your robot is somewhere. You want to pick what is the reference state on that reference trajectory that I want to get back to, right? So you're like, that's the path you're supposed to follow. You've fallen off the path. You want to get feedback to get back to the path. So you have to figure out what point on the path you want to return to. You're going to figure out what the error is between where you are and that desired point. And then you're going to try and compute a control law that is going to get you back to that point, right? And we'll go over each of these in sequence, but intuitively, the first thing is coming from planning. The second thing is saying, like, pick a point on the trajectory you want to get back to. Third thing is saying, figure out the difference between where you are and where you want to get back to.